Time for us to do some practice involving series, which means we get to look at adding together infinitely many terms. We're going to be focusing on two series in particular, geometric and telescoping. And spoiler alert, the majority of the time whenever you see a problem that says find the sum of an infinite number of terms, it's going to be something that's geometric or telescoping. So make sure you get really comfortable with using those. And the way you get comfortable at using tools is to practice. The more you practice, the better you get, the more comfortable it becomes. So do as much as you can. If you're following along, make use of the pause button. If you see a problem, try it out yourself first. Can you see what the right tool is? Do you see how to apply it? And soon, you'll be amazing. You'll be coming up with new problems. And you'll be having fun. Yes, you can have fun doing math. It becomes puzzles, solving things, and enjoying it. Well, let's begin. Our first problem, we want to find the sum from 0 to infinity of minus 2 to the power k over 5 to the power k. Well, what can we do? We want to sort of recognize what kind of sum it is. Now, the fact that we're asked to find it says, well, it's got to be something we can find, which, okay, probably something geometric or telescoping. Now, notice they're both to a power. So we can say, hey, this is the same as the sum, k equals 0 to infinity of minus 2/5 raised to the kth power. All right, well, great. Now we see it's definitely of a geometric sum, because when you see a constant to the power k, where k is your index, and that's it, right? Well, that just really says you're multiplying at every stage by another term here. Essentially, we keep multiplying by negative 2/5 to higher and higher powers. So it's of the right form. And so, what's the right way to do it? Well, remember, a sum of geometric series is a over 1 minus r. Now, what are a and r? A is your first term that you have, your first number, and then r, this is your multiplicative factor, what you're multiplying by at every step. So once we have these two pieces, we're good to go. Life is good. Now, what's our first term? 0. Plugging k equals 0, minus 2/5 to the 0 is 1. So this is 1 over 1 minus, and r, that's what's being raised to the k. So minus 2/5. Well, okay, so that's really 1 over minus makes a plus, 7/5, which makes it 5/7. And we're done. Now, there is one thing we should have done, and we probably did it up here, but let's at least express it. And that is, did we, well, maybe, were we? Were we okay in this step? Now, you said, yeah, you wrote it down, Steve. You must be okay. What's your concern? Well, remember, when we're talking about this sum, this is equal to the sum from k equals 0 to infinity of ar to the k if our size of r is small enough. So one thing we should have said, and we'll say it now, is this is a small number. Negative 2/5 is small enough, and therefore this is a valid step. And so, good, we're done. Woohoo! Wow, geometric series. We like them. They're easy. Good. We should have lots of problems with geometric series. Well, of course, we can't have all geometric. We've got to balance it out, but we'll probably have some more. Next problem. Find the sum from j equals 3 to infinity, 3 to the power j plus 2 over 4 to the power j. Now notice we're using different letters for our indexing, and this one says, look, use j. Is that fine? Yeah, no problem. Piece of cake, piece of cake. Now, it's trying to obfuscate things a little bit, but we're not going to get too worried. Say, look, before we go too far, let's just rewrite it in the way that we're comfortable. Okay, so what can we do to rewrite this in a way that makes us more comfortable? So one thing we can do is say, look, if we have 3 to the power j plus 2, it's the same as 3 to the power j times 3 to the power 2 over 4 to the power j. Because addition in the exponent means you can separate it as multiplication. Now, 3 squared, also known as 9. So this becomes the sum, 3 to infinity, of 9. And then we have 3/4 to the power j. Because we have 3 to the j upstairs, 4 to the j downstairs. We want to write it in the right form so we can easily identify what our pieces are. Okay, well, is it geometric? Yes. We see is some number times this term to a power. That's geometric. So, what do we get? Now, the temptation is to say what? Well, you might think, hey, this is a, right? Because, we think of it as a times r to the power. Be careful. Be careful. I think that they might have done something to throw us off. Notice, though, where we start. We start at 3. So what can we do? Well, what I like to do is say, I remember what a is. So when I think of my a, this is my first term. In other words, what would I get out at the very beginning? So what I get out is what I'd have when I plugged in 3. So this would be 9 times 3/4 to the 3. Divide that by 1 minus, now r, okay, that's our multiplying factor. So that's the 3/4. So what you see raised to a power, okay, so that's 1 minus 3/4. Great, well, that's not so hard to work with. 1 minus 3/4 is 1/4. That's downstairs. You flip it over to bring it upstairs, it becomes a 4. So we really have a 9 times 3/4 cubed times a 4. Well, okay, so that's really 9 times 3 cubed. All right, well, we can do that, right? So we have 9 times 3 is 27, times another 3 makes 81, times another 3 makes 243. Okay, great, 243. Downstairs, what do we see? Well, 4 cubed, but there's a 4, so we really get 4 squared downstairs because we can cancel off a 4. So 243 divide by 16. And there we go. There we are. That's the answer. Beautiful. Now, this one is, I think the moral for this one is be careful, right? Be careful in the sense that what is a? Oftentimes, we might be tempted to say, oh, that's a. No. A represents the first term. If there's been a shift in our index, we've got to be careful that we appropriately account for what's happened to that shift in our index. Because what do we want? We want to make sure we get the right answers. That's important to us because we like to make sure we understand what's going on. Yeah, that's actually really important, right? We really do want to understand what's going on. Good. Well, keep going, right? More problems. More problems. Oh yeah, there's always going to be more problems. All right. The next one. Find the exact value of the sum n equals 0 to infinity of 4 to the n plus 5 to the n plus 6 to the n over 10 to the n. And, what do you do here? And what's the right procedure to make progress going forward? Well, what we have to do is be a little bit careful here. What do I mean? Well, you might be tempted to say, oh, hey, 4 to the n plus 5 to the n plus 6 to the n, isn't that just the same as 4 plus 5 plus 6 to the n over 10 to the n? And the answer is no, that's not how it works. Exponents and addition don't really mix well. So, what can we do? Well, we're going to make use of this really wonderful tool, and it's called addition. It's been a fantastic tool, especially as long as it's upstairs. Downstairs, terrible. But upstairs, good stuff. Now, what do we mean? Well, what we mean is say, look, let's think of this as pieces. So 0 to infinity of 4 to the n over 10 to the n, and then 5 to the n over 10 to the n, and 6 to the n over 10 to the n. And more particularly, say, look, instead of thinking this as one sum where each piece has 3 parts, we can break it into 3 sums and see what happens to each one of them. Now, you might say, are we allowed to do that? And the answer is yes, as long as everything converges at the end. In other words, as long as the individual pieces converge, then when we combine things together, it converges. This is essentially what we're using as properties of limits here. So we say, think of this now as 3 sums. So the first one, 4 to the n over 10 to the n. So I'm going to rewrite that as 4 over 10 to the n. And then the second one, the sum, and that's going to be 5 to the n over 10 to the n. I'll write it as 5 over 10 to the n. And then the last one, the sum of 6 to the n over 10 to the n. I'll write that as 6 over 10 to the n. Okay, well, let's keep cleaning that up. See, 4 over 10, that can be simplified. They both have factors of 2. So that's 2/5. 5 over 10, well, that's actually really clean. That's also known as a half. Okay. And then the last one is what? Well, it's 6 over 10, factors of 2, 3/5. And now, we're like, perfect. Each one of these is geometric. Each one has a value of r, that multiplying factor, that's smaller than 1 in size. 2/5, a half, 3/5. All those are below 1 in magnitude. So, what's the first term? Well, n equals 0. 2/5 to 0 is 1. Here, half to 0 is 1. 3/5 to the 0 is 1. So it's going to become 1 over 1 minus 2/5. That's the first sum. 1 over 1 minus a half. That's the second. And 1 over 1 minus 3/5. That's the last one. Now, if you multiply the first, top and bottom, say 5 over 5, what do you see? You get 5 upstairs and 5 minus 2 downstairs. So that's 5/3. Here, multiply top and bottom by 2. Give your fractions, it'll be 2. And there are 2 minus 1. So plus 2. Here, multiply by 5 again. 5 minus 3. So 5 halves. So, all right, 5/3 plus 2 plus 5 halves. Common denominator would be 6. So we can write that as 10 over 6 plus 12 over 6 plus 15 over 6. And 10 plus 12 plus 15 gets us to 37/6. And we're done. That's it. Wow, beautiful. Beautiful problem. Cool. And it's just a really nice idea saying, look, let's break things into part. Each part we can handle. Each part is geometric. And life is good. All right. Well, let's keep going. So, our next problem. For size of x less than 1. So in other words, I'm thinking of x as some unknown quantity. If you want, you can think of it as a variable. Or you can just think of it as like, well, it's just some number which happens to be small. We want to find the sum from 0 to infinity of minus 1 to the power n over x to the power 2n. Now, when we look at a sum like this, our instinct says geometric. Now, the reason we think of it as geometric is we see things raised to the power n. And so geometric says, oh, when you have things raised to the power n, that's what we should do. Okay, geometric. All right, great, great. So in order for us to apply our technique, what do we need to do? Well, we want to rewrite our sum so we have just one term raised to the power n. So what can we do here? Well, we can say, look, another way to think of this sum, this is the sum n equals 0 to infinity of minus 1 to the n. That's fine. Here, the problem is x to the 2n. See, right now, the exponent is 2n. We just want n. But, here's the thing. X to the power 2n, we can think of that as x squared to the power n. Now, we still aren't quite ready, but we can combine these two terms together because you have something to the n times something to the n. So that becomes the sum, n equals 0 to infinity of minus x squared to the power n. Now we're like, perfect. I have something geometric because it's something to the n. Now, think of it again, even though it's like minus x squared, what is that? Just think of it, it's like, it's something. It's something to the n. If I chose x, then I have a number there. So right now I'm thinking of it as a number. Okay, now, can we apply our formula? Well, we need to check, is minus x squared less than 1? Well, note that minus x squared is the same. The minus doesn't make any difference as, and I can pull the square out. That's the same as just absolute value of x squared. But we know absolute value of x is less than 1, so that's less than 1, which means it's perfect for us to apply the formula for summing a geometric series. The first term, corresponding to n equals 0, would be 1. So we're going to get 1 over 1 minus, and what we have being raised to the nth power, that's our multiplicative factor, is minus x squared. So we end up with 1 over 1 plus x squared. That's it. We're done. Wow, cool. Now, you're probably like, ooh, we've seen 1 over 1 plus x squared before. And we know that, Steve, you have an unhealthy fascination with this function, don't you? Well, maybe not unhealthy, but I certainly enjoy it. And yes, this is a foreshadow of things to come. We're going to come back to this. And it'll take a few sessions to get there. But there is something interesting going on here. So, all right. More to be done, right? Yeah, of course. There's always more to be done. Okay, well, let's keep going. Our next problem. Find the sum, n equals 1 to infinity, of 1 over n times n plus 1. Okay, well, first off, let's be absolutely clear. This is not geometric. You can quickly rule things out as being not geometric if there's nothing raised to the power n. And in this case, nothing is being raised to the power n, so we are good to go. Definitely not geometric. All right. Well, what is it then? Well, if it's not geometric and we're asked to find, and we are asked here to find what we're looking for, our only other hope is telescoping. So when we're thinking of telescoping, what we should think of is like the individual terms. There's somehow we're going to get some cancellation when we look at things going and combining. And to get cancellation, we really want to say, oh, there's like something minus something. And that's not what we have here. We have 1 over n times. There's only like one term. There's not like something minus something here. What's going on? What's going on? All right, so let's get into it. First off, think about the ideas. We have this infinite sum, and suppose I said it's not a sum, it's an integral. In particular, suppose I said, oh, what's the integral of 1 over x times x plus 1? What would you do? What would be the right technique there? And the answer is, well, oh, we do partial fractions. That's how we do these kinds of integrals, right? Yeah. But now say, look, integration and summation are very similar. So if we did partial fractions in one case, we can definitely do partial fractions in another case. So I'm going to do partial fractions with this expression. So 1 over n times n plus 1. All right, something over n and something over n plus 1. Clear your denominator. 1 is a times n plus 1 plus b times n. And now choose wisely. So for example, if you choose n equals 0, what do you come to the conclusion? You come to the conclusion, look, 1 equals a. Now you might say, wait, hold on. How can I choose n equals 0? N goes from 1 to infinity. Why am I allowed to choose n equals 0? Because right now we're just thinking of n as a variable, and it's a free choice. In other words, it can be any number we want. It doesn't even have to be a whole number. Literally, it's any number we wish to choose at all. And so we just choose convenient numbers. If we choose n equals minus 1, you'll say, that gets that term to cancel. 1 equals minus b, or b equals minus 1. So we say, wow, that's really 1 over n minus 1 over n plus 1. So we have the following. This is equal to the summation n equals 1 to infinity of 1 over n minus 1 over n plus 1. Great. Now, this feels more telescoping because we see there's a difference. The real key to be telescoping is that you say, compare the terms. They should look like each other, except there's been a shift. Well, what do I mean by a shift? So it's like n versus n plus something. In our case, we say, n plus 1. A shift of 1. Okay, so wonderful. If there's a shift of 1, what that means is that if we go and compare one term over, cancellation should occur. Okay, so we see, starting with n equals 1, this is 1 over 1 minus 1 over 2. And then the next term, n equals 2, 1 over 2 minus 1 over 3. And the next term, 1 over 3 minus 1 over 4. And the next term, 1 over 4 minus 1 over 5. And oftentimes we just have to go far enough to be convinced that there's a pattern. Well, I'm pretty convinced already. We see because of the shift of by plus 1, that says I only have to compare one away. So we see, look, minus a half plus a half, cancel. Minus a third plus a third, cancel. Minus a fourth plus a fourth, cancel. And we see that. And the other thing to observe is note that these pieces are going to 0 as n goes to infinity. Now that's important because technically what we do is we say we're going to look at the sum up to some stopping point. So in other words, we're going to look at the partial sums. And so what happens is we get tons of cancellation except for the last terms on the ends. So we have this 1 over 1 and on the far end 1 over something. But it's 1 over a big something. That says that piece on the end goes to 0. So we're going to be left with 1. And we're done. So we're okay here because as our pieces went off, look, the pieces here, they went off to 0. Oh, great. And it just says it's only the first term that matters, so we're good to go. All right. Well, that's not so bad. That was actually kind of fun. We should do another one. Of course. Of course. All right. So, find the sum from 1 to infinity of log of 1 plus 1 over k. And now we're like, what? Okay. It's not so clear this time, right? I mean, how do we go about it? Well, we know we have to do something, and we can definitely eliminate some possibilities. We can definitely eliminate that this is not geometric, right? It's definitely no geometric sum because there's nothing to the power, right? If it was geometric, we'd have something to a power, where the power depends on the index. That's not here. So we've got to look for something else. So we say, okay, let's think of ways to rewrite it. And in particular, what we really want to get is something minus something, where we see an offset going on. Well, okay. So what do we see here? All right. Well, one thing we can do is we can look inside of the log. I mean, there's not a lot we can do, because remember, log does not break up over addition. But at least we can say, look, let's at least take the two terms in the log and write them as a single ratio. So in other words, common denominator. So here you'd have k over k and 1 over k would make it k plus 1 over k. Okay, that's true. That's what you'd get. And now we say, oh, logs. There's something nice about division. When we have a division inside of a log, it really becomes subtraction. And we want subtraction because that's telescoping. Telescoping says we have a term subtracting from one another. So this looks like k equals 1 to infinity of log of k plus 1 minus log of k. And now we're like, wow, perfect, great. These are the same basic function except an offset by 1. Now, what's going to happen? Okay, so if we start writing things down, we say, look, log of k equals 1, so it would be log of 2 minus log of 1, and plus, then k equals 2. Next term would be log of 3 minus log of 2, and the next term would be log of 4 minus log of 3, and so forth and so on. And now, at this point, we're like, perfect. We see what's happening. There's that offset of 1, and we say, look, the log 2's cancel, the log 3's cancel, the log 4's cancel, dot, dot, dot. The only thing that didn't cancel was the log 1, right? So this looks like minus log of 1, which is 0, right? Right? Be careful. Okay, all right. The answer, by the way, is not 0. No. You have to be careful. Now, you might say, but wait, isn't it? Because like everything else was being knocked out. And this comes to the point that you have to say, what's happening to your pieces? It is true that these are offset. That's great. So the fact that they're offset, that does say telescopes. Okay, so we do have that. But there's one other thing to keep in mind. You look at what the behavior is as you tend to infinity. What happens to log k as you tend to infinity? It gets big. It gets infinitely big, actually. It goes off to infinity. So what does that tell us? Well, what it tells us is that the end is not something we can ignore. In fact, the end is getting huge. So we have to pay attention to it. So what's really going to happen here? So what we really should have done is, once we see this goes to infinity, then the answer says, look, it's going to diverge. This diverges. But let's do it a little bit more proper. So if you look at this sum from k equals 1 up to some stopping point of this expression, well, what will end up happening is that you get lots of cancellation, just what you see here. What doesn't cancel is the minus log 1 from the first term and the last term, which would have plus natural log of n plus 1. See, the idea of telescoping sums is that when you put it all together, you get lots of cancellation except for little bits on the end. So there's a little bit of stuff here on the end. And now you say, great, well, log 1 is 0, that goes away. To see what happens as you we want to do this infinite sum, so we say now let capital N go to infinity. This goes to infinity as capital N goes to infinity. And therefore, it's an infinite sum. This, by the way, it's another example where if you look at it, it says, hey, if this sum is taken, the terms are getting closer to log of 1, which means the terms get close to 0. So this is a sum where the terms get close to 0, but the whole sum, when you add them all together, it gets arbitrarily large. So be careful. Just because the individual pieces go to 0 doesn't mean that the sum is going to be finite. Okay. Let's do one more. Let's do a nice cool down problem to finish up. Okay. Find the exact value of the following sum. Sum from 1 to infinity of 1 over pi to the n minus 1 over pi plus 1 to the power n. Now, question. Is this telescoping? And why not? Here's the thing. When we write problems as calculus instructors, I'm going to let you in on a little bit of sort of mentality that we have. We know what you know because we taught it to you. So we know what you're looking at, and we know sort of your mindset. And so we know your biases, and we know what you're looking for, and maybe what you're not paying close attention to. But now here's the good news. Now you know that we know what you know. And of course, it goes back and forth. See, we know that you know that we know what you know, and so forth and so on. So it's this fun game. Okay, can we make you think something looks one way when it's actually another way? So this is a problem which was on, I think it was on an old exam. And we're going to work it out. But before we work it out, I just want to point out, it feels like telescoping, right? Because what do you feel like you should be looking for? It's like, oh, I should look for something that's being subtracted, and then I should be looking for something which is shifted. So it's like, oh, isn't that what's going on here, where I have some things being subtracted and there's a shift? But here's where you have to be careful. Where's the shift happening? When we talk about our shift in terms of telescoping, the shift has to come with the index, so like n versus n plus 1. But notice the shift is attached to the pi. Pi versus pi plus 1. The n's are the same. This is not a telescoping. In other words, if I replace n by n plus 1, I don't get that expression. What is it, though? It's geometric. Why? Because think of it. Look, just cover up this piece. It's 1 over pi to the n. That's something raised in. N is up in the exponent. So usually when we see n upstairs, that's the signal, hey, this is going to be geometric. So I say, oh. In fact, what we can do is we can break it up into two pieces. So 1 to infinity of 1 over pi to the n minus 1 to infinity of 1 over pi plus 1 to the n. We say, look, each one of these is geometric. And in fact, let's do one more step before we write down what they sum to. Really make it clear. So it's 1 over pi to the power n. And it's also, this other term will be 1 over pi plus 1 to the power n. Now, we say, okay, yeah, this looks geometric. Everything looks great. Ah, boy, they were being a little tricky here, but all right, we finish up. We're starting with n equals 1. So we look at the first term. The first term we plug in n equals 1 would be 1 over pi. And then you divide by 1 minus what you multiply by. So in this case, 1 over pi. Minus, okay, here, the first term, plug in 1 over pi plus 1. Divide by what you multiply by, which is this 1 over pi plus 1. And notice that 1 over pi and 1 over pi plus 1, they're both below 1. So the formula holds. Now in the first case, we can multiply top and bottom by pi. And if we did that, we'd have 1 over pi minus 1. Here, multiply top and bottom by pi plus 1. You have 1 over pi plus 1 minus 1. Well, that's going to simplify it to be pi. All right? Pi plus 1 minus 1. And we can even get a little bit further. We can get common denominator, so multiply by pi minus 1 over pi minus 1 times pi. So here I multiply the first term by pi over pi. That's where that pi came from. Second term by pi minus 1 over pi minus 1. That's the second term there. And now we say, wow, the pi's cancel. So we end up with 1 divided by pi minus 1 times pi. And we're done. We're done. All right. So I think the word of warning here is be careful. Don't try to rush into a problem before you make sure you understand what type of problem it is. It's not so hard to spot geometric sums. Geometric sums are some constant number to like the index, so n or j, whatever your index is. Telescoping sums can be a little bit more cryptic, and essentially you should think, is this geometric? Yes or no. If it is, okay, great. If it's not, all right, try to say, can I rewrite it in a nice way where it telescopes? In other words, two expressions which are essentially the same except for a shift. And once you have that, you're good to go. Life is good. Well, good. Thanks for joining, and hope to see you again. Bye.